Hi, thanks for the introduction. Okay, so this is parameter-free online convex optimization with sub-exponential noise. This is joint work with Francesco Rabona. So the main theme of this talk is doing online convex optimization with noisy gradients. Let's review the standard setting. We have a learner and adversary. At time t, adversary sets the loss function LT, and the learner predicts WT, suffers a loss, and then receives a sub-gradient descent. And the learner hopes to suffer as least loss as possible. And we measure the performance by regret, which measures how far you are from a fixed competitor U in terms of loss. And here we don't impose any restriction on the U. So this is called the unconstrained OCO problem. So in this work, we assume that the gradients are corrupted by some noise. And this is pretty natural setting, right? Many times real-world data comes through a noisy channel. But a striking example is differentially private subgradient descent, where each gradient is sort of sanitized by adding some noise so you can protect privacy. I'll talk more on this later slides. So we make the assumption on the noise, sub-exponential. It looks as follows at the top. And it includes not only Gaussian, but also Laplace and chi-square distribution. One thing to point out is the gradients are now noisy. So the iterates WT are stochastic, and regret is also stochastic. So we consider expected regret. Okay, so why is this an interesting problem? Why don't we use existing algorithms for this setting? Indeed, you can just feed in those noisy gradients to online gradient descent without projections. And you can just read off the regret bound, just take expectation. You get the following regret bound, which is essentially the norm of the competitor squared times root t. But we're not satisfied because we know that it is possible to get, in the standard setting, norm times root t instead of norm squared. But then why don't we use those near optimal algorithms here? Turns out we cannot use them because they assume they require that the input gradients are bounded. Okay, and indeed, recent lower bound result says if your algorithm handles unbounded gradients and if it has the right dependency, near optimal dependency on the norm of the competitor, then you are bound to suffer exponential regret. So this just tells us that we cannot just use existing algorithms to achieve the desired regret bound. So we need a new algorithm. So the main question we are after is, can we achieve the same optimality as in the standard setting with respect to the norm of the competitor and the time horizon t, despite the fact that the observed gradients are noisy and unbounded? And the answer is yes. And we propose new algorithm called betting algorithms for noisy coins, Banco in short, and Banco is bank in Italian. It's pretty clear I didn't name this algorithm. My co-author Francesco did for the love of coins. So we do achieve the desired regret bound with respect to the norm and the time t. And we show a lower bound that matches up to logarithmic factors. And there are two good things about our algorithm. First, it is parameter free. What it means is that it can adapt to the norm of the competitor, which is unknown beforehand, without tuning parameters. In contrast, if you run stochastic gradient descent, then you cannot do that. You have to run it multiple times with different running rates to achieve that bound. And second, we achieve generality. So we use the reduction. So Banco is in fact a 1D algorithm, so it's one-dimensional case. But instead of extending it to multi-dimensional space, we do the reduction, extending the prior work, so that it'll take in an algorithm in Banach space that competes within a unipole. So this is constrained version. But it takes in that algorithm and turns it into the one that can compete in the unconstrained space. So it can compete with any vector in the entire space. And that's possible because we have the following regret decomposition. And turns out Banco can carry all the burden of adapting to the unknown gradient, unknown norm of the competitor. And the black box algorithm is just doing its own thing, thinking that it is competing with the uniform competitor. So before going any details, let me just summarize what's going on. Our paper has three components. First, we have the algorithm Banco and the reduction. Second, we have an application to differentially private SGD. And third, we have a connection to concentration of measure. Okay, so for the remaining talks, I'll briefly touch upon key ideas of each component. So first, how did we build Banco? So this is the line of research where we want to connect how the game of coin betting is related to convex optimization, online convex optimization. And so it starts by the following game where imagine an adversary, and the adversary sets the coin flips, heads or tails, but he does so arbitrarily instead of actually flipping a coin. And you, as a gambler, decides which side to bet and how much. Okay, and then if you're correct, you make the money. Otherwise, you lose the money, and you repeat. And turns out in this game, if you have a specific betting algorithm that has a guarantee on how much money you can make, then it automatically implies a online convex optimization algorithm with a specific regret guarantee. So we use this framework, and we take these results into the world of noisy coin flips, and we show that all these relationships still hold true, but now in expectation. Okay, so that's the key idea. And you can see our algorithm in the middle. It's involving some integral, and there's a function that looks like Gaussian distribution, but we can simplify it to the equation at the bottom. Okay, so next application, locally differentially private SGD. So here, stochastic gradients are already noisy, but they are coming with another layer of noise to keep the privacy. And the specific condition required is epsilon locally dp. And again, we improve the dependence on the norm. And also you can see that the factor d over epsilon, and that's the price we pay for keeping the privacy. And here in this regime, ours is the first parameter-free algorithm. And that's important in this setting because whenever you request a gradient, it is costing privacy. And so does parameter tuning. So in the case where you are given a fixed budget of privacy, then when compared to stochastic gradient descent that requires repeated running with the tuning, our algorithm can only run once, so we get to use a larger epsilon. So larger epsilon means less noise and faster convergence, as you can see from the convergence rate here. And finally, we have a connection to concentration of measure. So without further going into detail, the top equation, that's the key property of a noisy coin betting algorithm. And GT is the true gradient, the expected gradient. And we can set that to 0. And you can see that we automatically get a super martingale. And it eventually leads to a concentration inequality for Banach-based smooth norms. And it has the law of the iterated logarithm type. And so we don't, okay, so the bound itself, we don't claim much novelty. I think the novelty is the connection from the coin betting algorithms. And our poster number is 167. If you're interested in, come talk to me. Thank you. Yeah.
So for ensuring privacy, you also need a bound on the gradient everywhere. So do you assume that you have a uniform bound over gradients everywhere?
We have bound on the expected gradients. But actually, observed gradients can be unbounded because these are coming with sort of exponential noise.
I see, but you don't necessarily then get like a fixed privacy, basically a privacy guarantee in this case.
Yeah, I'm not sure. I think we just use this epsilon dp criterion to set up the right parameter for the exponential distribution on the noise. And that just comes into the, yeah, we can chat offline.